for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. Today we are going to study. I am going to start isomerism. This particular topic, I'll take at least two lectures on this topic, and this topic is very important for you and for anyone who is preparing for JEE or NEET. And before we go into the isomerism, if you remember few things, we have seen few chemical compounds with the same empirical formula but different molecular formula, and these compounds are different because I have explained earlier that they are having different molecular formula. And for example, if you see the molecular formula of acetylene C2H2 and benzene C6H6, these compounds, if you get the empirical formula of both the compounds, the empirical formula will be CH. So C2H2, the empirical formula will be CH because you have to divide all the numbers of subscripts by 2. In the case of benzene, we have to divide the subscripts by 6, so it will again be CH. But in the case of empirical formula, if you look at the empirical formula, you may not distinguish between these compounds, whether it is acetylene or the benzene. Similarly, you can have another set of compounds, the C2H4 or C4H8. The empirical formula of both the compounds will be CH2. So based on the empirical formula, just by looking the empirical formula, you may not recognize, you may not understand their different compounds, but from the molecular formula, we can recognize, we can easily understand that they are different compounds, and so their properties will be different. However, if you go further deeper, you can see that the compounds with even with the same molecular formula may not be the same compounds. The same different compounds may have the same molecular formula, and and such phenomena is called isomerism. For example, if you see these compounds NH4CNO and another compound NH2CONH2, these are two different compounds. This is an inorganic compound made up of ammonium ion and cyanate ion. This is ammonium cyanate, and this is urea, an organic compound. NH2CONH2. If you look at the structure of this compound, this carbonyl group CO is connected to two NH2 groups, and here it is NH4 plus ion and CNO minus ion. So no, there is only one carbon nitrogen bond, and that nitrogen is not attached to any hydrogen atom. So just is not attached to hydrogen atom, so they are different compounds, and so their properties are also different. And we know ionic compounds and the covalent compounds are different compounds. They are in different compounds. Their bonding is different, and thus they are having different type of bonding, and so their properties will also be different. And such phenomena, as we know, so the existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism, and such compounds are called isomers. And so such compounds are called isomers. These are two isomers. Although these examples of isomers we see in plenty in organic compounds as well as in coordination compounds. The isomerism in coordination compounds we will see later in the chapter coordination compounds. Isomerism in the case of organic compounds we will see here only, because we have started the chapters or the basic concepts of organic chemistry. And so since we know what is isomerism, so two different compounds having same molecular formula, the phenomena is isomerism, and these two compounds are called isomers. The isomerism, there are different types of isomerism, the structural isomerism and stereoisomerism. As it appears from the name itself, structural isomerism means there will be difference in the structure. So two compounds having same molecular formula having different structures. So they are called structural isomers, or the phenomena is structural, and the phenomena is structural isomerism. Stereoisomerism, to understand the stereoisomerism, we have to go further deeper, and further deeper means just by looking at the structure, you may not understand these compounds are different. But if you look further deeper, you can see that these compounds, certain compounds, different groups are attached in different orientations at certain positions, and certain carbon atoms or maybe the nitrogen atom. And such isomerism is called stereoisomerism. So stereoisomerism is the structure will appear to be the same, but what you will see, the attachment of the different groups in the two different compounds will be different, and because of the orientation of the different orientations of particular group or the two groups, you will see the different properties in the certain properties of these two compounds will be different, but their structure will be same, molecular formula will also be the same. The structural isomerism is of four types. Basically, we classify it in the four different groups: the chain isomerism, position isomerism, functional group isomerism, metamerism. However, we also talk about some more type of structural isomerism. Although in the strict terms you may not say them as structural isomerism, but the tautomerism and the ring chain isomerism are also called structural isomerism. So similarly here, you may not tell them as exactly isomers people, but they are isomers because they are different compounds. So strictly saying the tautomerism because one compound is having two different structures and these two different structures are in equilibrium. So this phenomena is type tautomerism. And that difference is only because of the position of hydrogen atoms. And because of the position of hydrogen atoms, the number of pi bonds and its location on the in the compound will also be different. And so the same compound is in two different forms, two different structures, as called tautomerism, and so those things we'll see later. So one can say maybe based on the stability and other things, these are physical states. And then the stereoisomerism are of two types: geometrical isomerism, optical isomerism. There is another kind of like conformational isomers people are also called, or the rotational isomers. So sometimes I have seen in certain books it is written that the conformations are stereo isomers. I believe they are not conformational isomers are not stereo isomers. The conformations are basically the different physical states of the same compound and they are basically not isomers. Although people they call them as the rotamers, you may call them rotamers or conformational isomers because the same compound is more stable in particular conformational state, that is the physical state, and less stable in another conformational state. However, both the states are of the same compound and so they give the same kind of chemical properties. However, again the conformational isomers has more implications and has more meaning in the case of very large molecules. In chemistry, we are not going to deal with those large molecules like proteins. The proteins in different conformations, they can have infinite conformations. And one of those conformations is the folded state of the protein, and so that is the most stable state. And other states are unfolded, and the unfolded states can have many conformations, and those things are not in our syllabus anyway. So we'll mostly focus on this part today: structural isomerism, different parts, and the stereoisomerism we will see in the next class. Again, let's see structural isomerism. Four types of structural isomers are chain isomers, position isomers, functional group isomers, and metamers. So chain isomerism, again, you don't have to remember all the definitions. Chain isomers, the difference in the chain structure. Position isomers will be for the position of a functional group in the chain. For the if it is different, it will be position isomers. Functional group isomers, compounds having same molecular formula but having different functional groups. And there are certain functional groups which are always isomers. If they are having two compounds having same molecular formula, they can have this pair functional group isomers pair like alcohol and ether. And metamers. Metamers, a particular atom is there, a heteroatom. Around that heteroatom, all the carbon chains, that if the carbon chains are different, then we call such isomerism as metamerism. Let's see one by one. Structural isomerism. Let's read its definition. So compounds having the same molecular formula but different structures are classified as structural isomers, and the different structures means what? Manners in which atoms are linked. So different atoms in the manner in which they are linked are different, and so they are structural isomers. So we will first see the chain isomerism because structural isomerism four types we have seen. The chain isomerism, when two or more compounds have same molecular formula but different carbon skeletons, and the different carbon skeleton, because of the different carbon skeleton, their chain is different, and because the chain is the highest, the longest chain is different, so they are chain isomers. So these are referred to as chain isomers, and the phenomena is termed as chain isomerism. The example C4H10. So C4H10, this butane or N-butane, this is one compound, and if I bring this CH3 group at the middle carbon here, and if I just connect this CH3 group to this carbon atom, to this hydrogen, I have to replace one hydrogen to here and CH3 group to here. So you can see this compound. CH3, CH, CH3, CH3. Why I have to just migrate one hydrogen to here just to keep the valency of carbon, but just to maintain the tetravalency of carbon atom. And so the CH3 group, you can see the number of carbon atoms in these two compounds are same, number of hydrogen atoms in these compounds are also same, but what you see here, the chain length is different. The longest chain is different. Here it is 4 carbon, here it is 3 carbon. And this how we will see, we'll start from one end and go to the another end and we'll find the longest carbon chain. This is 3 carbon chain, this is 4 carbon chain. The common name of this compound is isobutane, but the IUPAC name what can use 2 methyl propane, and this is butane. Simply, this is butane, this is 3 methyl propane. So these are two different compounds. For the C3, the propane, the compounds with the 3 carbon atoms, C3H8, we won't see any isomerism because C3 here only. This CH3 is also hydrogen. Even if you bring this hydrogen here, it will give the same compound. Only the difference will be, it will be in the different conformation, and the conformations are not isomers. We will see some 10 examples. So now compound with the molecular formula C5H12 represents three compounds. This example is this CH3, CH2, 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 CH3. So 5 carbon atoms and then hydrogen atoms accordingly we will put to saturate the valency of all the carbon atoms, and that is the tetravalency, and so we'll get this structure. So 3 hydrogen atoms to this terminal carbon, 3 to this terminal carbon atoms, and all the intercalary carbon atoms will contain 2 hydrogen atoms or will be linked to 2 hydrogen atoms. Now just bring this CH3 group to any of the carbon, this carbon, this or this. So just this CH3 group to here. So this compound you can see the numbering now here will start from here 1, 2, 3, 4. So only the longest chain is having 4 carbon atoms. Here the longest chain is having 5 carbon atoms. So this is pentane and this will be the root, will be for the butane. However, the common name is isopentane, but the IUPAC name for this compound is 2-methyl butane. So 2-methyl butane is the IUPAC name of this compound. The longest chain is having only 4 carbon atoms. Now what can again one can do is bring this CH3 group to here and the hydrogen to here. So this compound, this is called neopentane, and neopentane IUPAC, the longest chain of this compound contains 3 carbon atoms, 1, 2, 3, or 1, 2, 3, or 1, 2, 3, any direction you can go 1, 2, 3, and so 2 methyl substituents are there at the second carbon atom. So the IUPAC name of this compound is 2,2-dimethyl propane. The common name of this compound is neopentane. Another thing is, if you bring this carbon atom to this direction, to link to this carbon atom itself, so what will it will be just a different conformation, or here in this side it will not be a different compound. Another thing is, if you just bring this CH3 group to this carbon atom, and the longest chain is still having 4 carbon atoms, then that compound will be the analog homologous to this compound. Actually, that compound will be the same as of this compound, so there is no difference. That compound's name will also be, if this CH3 group was here, suppose, so that this compound's IUPAC name of this compound will still be 2-methyl butane. So they are not isomers; they are the same compound. So similarly, you can see different examples of chain isomerism. So chain isomerism is what? The carbon skeleton is different, and carbon skeleton is different means the number of carbon atoms in longest chain is different, and the number of carbon atoms in longest chain, you can see they are different in these two compounds, and they are also different in these three compounds. But molecular formula of all these three compounds is same. It is C5H12, and the molecular formula of these two compounds is also same. It is C4H10. Let's see this question. Do the following compounds for chain isomerism? So this compound and this compound. So the answer is no, they are not. They do not show chain isomerism because they are the same compounds. Only thing is they are in different conformations. So this CH2 group, what I have done is this CH3 group which was here in this, I have just bring to this side, and this CH2 I have brought to this side, and just have rotated the entire molecule like this. So this is actually what is there. This is the same compound, and so the longest chain. Another way to find out whether they are the same compound or they are having the same chain or not. So what will you do? You will just calculate or find out the number of carbon atoms in longest chain. We start with one terminal and go to the another terminal. So one, two, three, four. Four carbon atoms. In this case, one, two, three, four. So we'll reach to another terminal and so the four atom carbon atoms here as well, four carbon atoms here as well. The hydrogen atoms are also same and the hydrogen atoms are also same. So they are the same compound, they are not isomers. Even if the compounds are having not are having different molecular formula, if the compounds are having different molecular formula, in that case they are not isomers. They cannot be called isomers because isomers is defined for only those compounds which are having the same molecular formula. Now let's see the position isomerism. The position isomerism, as I said in earlier, the position isomerism is mostly because of the position of the functional group in the chain of the longest chain of the organic compound. If the position is different, then we can call them the position isomerism. So when two or more compounds differ in the position of substituent atoms or functional groups on the carbon skeleton, they are called position isomers, and this phenomena is termed as position isomerism. So what they do they differ in the position of substituent atoms or the functional group on the carbon skeleton. So this molecular formula, the compound with the molecular formula C3H8O, this O oxygen atom. So this represents two alcohol, and the alcohol is the molecular is the functional group in this case. The OH is the functional group, and so these are two compounds. This of the carbon skeleton, the longest chain still contains three carbon atoms in both the cases. So the chain length is not different, so they are not chain isomers. But what do we see the difference is the OH group is attached here to the terminal carbon atom, and in this case it is attached to the middle carbon atom. And so the numbering, if you start the numbering of to name this compound, to give the IUPAC name of this compound, the numbering will start from here 1, 2, 3. In this case, numbering can be started from this end or this end 1, 2, 3. So the here in this case, in this compound, the OH group is attached to the first carbon atom, and in this compound, OH group is attached to the second carbon atom 1, 2, 3, and so they are position isomers because their position of the OH group on the carbon skeleton is different. Here it is on the second carbon, here it is on the first carbon. So this is called the propane 1 all or 1 propanol. You can also say 1 propanol, and this compound is 2 propanol or propane 2 all. Diopsy. Similarly, for with the substituents, we know some of the functional groups that we have as a substituent. The halo group, nitro, we treat them as the substituents. So this bromine compounds with the bromine or the bromo functional group or the bromo substituents. And so you can see here in this compound, the bromo group is the numbering will start from this carbon atom, the carbon atom which is linked to the bromine, because we want to give this bromine the lowest mm, position. And so in this case numbering like this example can start from here to here, this end or this end. So let's see if we do the start the numbering, do the numbering from this end to this end 1, 2, 3. So bromine is at the second position, here the bromine is at the first position, and so this compound is 1 bromopropane and this is 2 bromopropane, and so both the compounds are position isomers. In certain cases, suppose this was CH3CH2Br. In another case, CH2Br CH3. In these two compounds, there is no possibility of position isomers. Both the compounds are same because the compound was having only two carbon atoms. And with these two carbon atoms, what can we do? The numbering will start from the carbon atom which is attached to the bromine. And so if this was CH2Br CH3, so numbering 1, 2. So this is bromoethane, and if this was CH3 CH2Br, so the numbering will start from here. So 1, 2, this is also bromethane. So this is also 1, 1, so there is no possibility of position isomer. So the position will not show in that case in IUPAC nomenclature because these compounds are having no position isomerism. However, if the two bromo groups are there, in that case, we will have the possibility of position isomers are there. These two bromine groups, they can be on the same carbon atom or uh, on the same carbon atom or on the different carbon atoms. So there is a possibility of position isomers, and in that case, in the IUPAC nomenclature, we will have to show the position of the bromine atoms. Now let's see this example. This example is also of the alcohol, And now see this carbon alcohol, the OH group is attached to this carbon atom, and so that this longest chain contains four carbon atoms. This longest chain also contains four carbon atoms. That they are not position isomers. Now the position of OH group, the functional group, we see it is different. Here it is on the first carbon atom. The numbering, as the numbering will start from here and will go in this direction. In this case, numbering will start from this direction. It cannot be started from this from this carbon atom, because if you start numbering from this carbon atom, OH group will be on the third position, and if you start from this, OH group will be on the second position, and we will have to give the lowest priority or lowest number to the carbon atom which is linked to the functional group, and so the numbering will start from here. So 1, 2, 3, 4. So this compound is what? It is 1 butanol or butane 1 all, and this one is 2 butanol or butane 2 all. Both the way of naming is uh, correct as per the IUPAC rules. Now let's see this example, another example. So these two compounds, this is CH2, CH3. One methyl group is here as a substituent, as a branch. In this case, the numbering, so the longest chain contains three carbon atoms and one methyl group as a substituent. In this case, 1, 2, 3, the longest chain here in this case also contains the three carbon atoms, and the methyl substituent is there at the second position. However, if you look at the numbering will be started from here 1, 2, 3. OH group is at the first position. In this case, 1, 2, 3. OH group is at the second position. So this compound is 2 methyl 1 propanol, and this is 2 methyl 2 propanol, or 2 methyl propane 1 all and 2 methyl propane 2 all. Now another example is this, the benzene with the benzene ring having one methyl and one Cl group, and a Cl group can be here Cl substituent on this carbon atom, or the Cl substituent can be here, here, or here. If this Cl substituent is here, they are all position isomers, and this position, this compound is chlorophenyl methane. This is treated as a substituent, this is also a substituent, and this chain contains only one carbon atom. So this is chloro substituent. There is no numbering because only means chain contains only one carbon atom. This is chloro. This is phenyl methane. Chlorophenyl methane. Here in this case, we know the numbering will start from this. One can do, because this is the base compound. One can consider the CH3 and the benzene pH, the phenyl ring as the base compound, which is called the toluene, and the chloro substituent at the second position. So this is chloro 2 chloro toluene. This one is 3 chlorotoluene. This one is 4 chlorotoluene. And so what you see, that the difference in the name is only because of the position. Only exception is here. So 2 chlorotoluene, 3 chlorotoluene, 4 chlorotoluene. If the compounds name are different because of this, and because of certain numbers of the substituents, all those compounds are what their position isomers. Let's see the write the this question. Write the structure. Write the structures of two ketones showing position isomerism. So what does it mean? It means position iso. The question itself gives one information. The ketones also show position isomers. We'll have to write two structures of the structures of two ketones showing position isomers. I have not made the structure. We'll see such examples which we have seen earlier in the nomenclature. For example, if you look at this compound, if this CH2 group, this CO group, carbonyl group was CH2 group, then we can have one ketone. And if this CHO group was CH2 and this was CO, then we can have another isomer. So we can have two different isomers just by making this carbonyl group as a CH2 group in one structure. In another structure, we can make this carbonyl group as a CH2 group, and then we can have two different structures, two different ketones, and their names will also be different. And the name, if suppose this was CH2 group, what will be the name? 1, 2, 3, 4, 5, 6. So it will be hexane 2-one. And if this was the CH2 group and this was still there, then in that case the numbering will start from here. 1, 2, 3, 4, 5, 6, because this carbonyl group should be given lowest number. So the numbering will start from this side, not from this side. So this will be hexane 3-one. So hexane 2-one and hexane 3-one are the position isomers having functional group with functional group with ketone as a functional group. Now let's see the functional group isomerism. So we have seen functional group isomerism. What the earlier, so two or more compounds having the same molecular formula but different functional groups are called functional group isomers, and this phenomena is termed as functional group isomerism. The same molecular formula but different functional groups. What is the compounds having same molecular formula but they are having different functional groups, and there we can have, we should have this much imagination, this one much understanding that which functional groups are compatible to form a functional group isomerism. So if you look at the aldehyde and ketone with the same molecular formula, they can be functional group isomers. Similarly, ethers and alcohols with the same molecular formula, they can have functional group isomers. And the way how it will be, the general formula, if you write the general formula of these compounds, the general formula of this compound is ketones and aldehyde. This is what this is in general, this C3H6O. This is also C3H63216O. So CnH2nO. CnH2nO is the general formula of these two functional compound of ketones and aldehyde both. In this case, what we will see, C1234 C4H10O. This is also C4H10O. So this is CnH2n plus 2O. So general formula is same. So the general formulas, if the general formula of two different functional groups or the homologous series is same, so there is a possibility of having functional group isomerism. If those compounds, those homologous series contain a functional group. Similarly, this esters, you can see the similar example. Let us now see this case in detail. So the propanone, this is propanone, the C double bond O, this is the ketone that we know, because this carbonyl group is attached to two different alkyl substituents, and this is aldehyde. This is aldehyde CH3CH2COH. This carbonyl group is attached to an alkyl group on one side and one hydrogen on the another side. So this is aldehyde, and they are having same molecular formula. So they are functional group isomers. And why there are different functional groups? Same molecular formula, functional group isomers. Similarly, ethers and alcohols with same molecular formula are functional group isomers. So the same, these are the same two compounds with the same molecular formula. This is alcohol, as you know, this OH, and the ether. And ether is what? The alcohol, what we see, oxygen is attached to one alkyl group on one side and one hydrogen atom on the another side. In ethers, what happens? Oxygen is attached to two alkyl groups on both on two sides. Like here, the similar difference you can see here. Ketones, two alkyl groups. Carbonyl group is attached to two different alkyl groups. In ethers, oxygen is attached to two different alkyl groups. Aldehyde, carbonyl group is attached to hydrogen and one alkyl group. In alcohol, oxygen atom is attached to one alkyl group and one hydrogen. So similarity is there. So these compounds are having two different functional groups. OH, alcohol is another functional group, ether is another functional group. And so there are different functional groups having same molecular formula. This is C4H10O, 3 plus 3 plus 4, so 10, C4H10 and O. This is also C4H10O. So this is one butanol or butane one all, and this is what? Ethyl, ethoxy. Up to here it will be ethoxy, and this is ethane. So this compound is ethoxyethane, IUPAC name of this compound. Now the carboxylic acids and ester with same molecular formula are also functional group isomers of each other. The carboxylic acid and esters with the same molecular formula. Here again we see the similarity. This COO group is attached, if COO group is attached to two different alkyl groups, or the carbon is attached, in this case may be attached to hydrogen atoms even, but this O is definitely attached to one alkyl group, and this carbon can be attached to a hydrogen or an alkyl group, then it is ether. And in the case of carboxylic acid, this O is attached to hydrogen atom, and so this is carboxylic acid. And if the carboxylic acid and ethers are having same molecular formula, they are functional group isomers, as you can see here. This is C3H5 5 3 H6 C3H6O2. C3H6O2. The general formula is what? CnH2nO2. CnH2nO2. And this one is what? C3 1 2 3 3 3 6 and O2. So this is also CnH2nO2. So the general formula is same, but they are having different functional groups, so they are functional group isomers. Such compounds with the same molecular formula will show functional group isomers. Now let's see the metamerism. Metamerism arises due to different alkyl chains on either side of the functional group of a functional group in a molecule. So this example you can see, for example, the ether. Ether O group is there, and on the O group, this C4H10O. This is a functional group. If this functional group oxygen is attached to CH3 group on one side and C3H7 group on the another side, there is one possibility. There is another possibility that this oxygen is attached to C2H5 on one side, another side also it is attached to C2H5. Similarly, if you bring one CH3 group again to the left hand side, it will give the same compound, this compound. So that is not a possibility. So there are two possibilities with this compound to have two metamers, and these metamers are the CH3O, C3H7, or C2H5, O, C2H5. And so they are two different isomers. And this isomer, so this because of this, they are different isomers, their name will also be different. And so this compound is shown here. This will be called methoxypropane. The longest chain is propane, and this is methoxy. And this is ethoxy ethane. So these are two metamers. Another example, this CH3, CH2, CH2, CH2O, CH3. And this is what, and then this O is what? If it is between this carbon and this carbon. First, here in this case, this oxygen atom is between this carbon and this carbon atom. In other structure, this oxygen atom is between this and this carbon atom. So this and this carbon atom. And so these are different compounds. Even if you bring this oxygen atom here between these two carbon atoms, it will give the same compound as this one. So that is not a different compound. So it will not be an isomer. So this there are two possibilities again with this molecular formula, and the molecular formula is what? C5H12O. This is also C5H12O, and this is what? This is ethoxypropane. This is methoxybutane. Four carbon atoms. Methoxy, three carbon atoms, and this is ethoxy. So ethoxypropane, methoxybutane, they are two different metamers, and this phenomena is metamerism. Now, as we have seen the examples of ethers, similarly another functional group is there which can also show the metamers, and these are the secondary and tertiary amines also show metamerism. And what are these examples? The amines, secondary amine and tertiary amine. The nitrogen group is attached, NH group is in the secondary amine is attached to different alkyl groups. So this NH group, and so you see this example. Is this NH is attached to one methyl group on one side and an alkyl chain with four carbon atoms on the another side. In this compound, the NH group is attached to C2H5, so one alkyl group with two carbon atoms, and this side it is attached to one alkyl group with three carbon atoms. The molecular formula of both the compounds are same. This is C5H12 H sorry, let me calculate. 1 2 3 4 5, and this is 3 plus 2 plus 2, 2 to 4 plus 3 7 plus 2 9 plus 1 10, and this is 13. So this is C5H13N, or C5H13N one can write as C5H12NH, and C5H12NH, this is also C5H12NH, and C5H12NH means what? One can write it as the CnH2n plus 2NH, and the general formula of secondary amine, and the general of secondary amines as they are showing metamers, and both the compounds molecular formula are same, but the alkyl groups that are attached to the functional group in this case are different, and these two alkyl groups are different. You can see their carbon chain length is different, so they are metamers. Similarly, esters also show metamerism, and these two examples are of esters which are metamers. And so, in this compound, the CH3 group is attached to one this O, and this is CH3CH2. Another example is CH3COOCH2CH3. What I have done, I have just brought this CH2 group from this side and put it here. So this is another ester, and the molecular formula is same, and so one can call them as also as a metamers. Another metamers will be, even if this CH3 group I bring here, another CH2 group from this, only hydrogen atom will be left, and put this CH2 group here. So HCOO CH2 CH2 CH3, there will be another ester, and that will also be metamers. So the esters also show metamerism. Please note that the ketones, double bonds and triple bonds do not show metamerism. Instead, they exhibit position isomerism. And why they do not show metamerism? Because as you see here, the metamerism, we see the carbon chain is interrupted by the presence of functional group. You are not counting all the carbon atoms in the longest chain. So this side one alkyl group, then this is interrupted by NH group, and this longest chain contains only four carbon atoms. Here in this case as well, in this case as well. And so, however, in the case of ketones, double bonds and triple bonds, the carbon atoms which contains the double bond or the triple bond are the carbonyl group in the ketones. They are part of the longest chain, and because since they are part of the longest chain, only their position can vary, and so they do not exhibit metamerism, but they show position isomerism. And so you may not, you should never be confused that the ketones will also show metamerism, as you can see here. The carbonyl group in this case here, and another case carbonyl group here. So in that case, these two compounds will be position isomers. They will not be metamers, because all the longest chain will contain all the carbon atoms here. Similar things you can see in the case of double bond and triple bond as well. Let's now see the tautomerism. The tautomers refers to the isomers of a compound. Although these tautomers, as I have said in the structural isomers categorization, we have not put tautomers, but the tautomers are there. So another type of structural isomerism people consider, many books consider it as the structural isomers. Tautomers are chemical compounds that are readily interconvertible and differ only in relative positioning of hydrogen atoms. So these tautomers, you can see the tautomers. So actually, it is what one compound, and one compound is having two different structures. The same compound having two different structures, and because the structure is different, so these compounds show a broad number of chemical reactions. In another structure, it will show some kind of chemical transformation, and with another structure, it will give another chemical transformation. So the tautomers refers to the isomers of a compound which only differs in the position of protons and electrons, and the two tautomers are always in equilibrium, and you can see the equilibrium sign here in all the cases, the example that we have seen. Generally, the tautomers a compound exist together in equilibrium and easily interchange. So they can easily be interchanged, and so they exist in equilibrium, and it occurs via an intramolecular proton transfer. And so the same molecule, intramolecular means the proton transfer means the proton transfer within the molecule. That is called intra. Intra means within. And an important example of this phenomenon is ketoenol tautomerism. The ketoenol tautomerism is the most important and most common tautomerism, and most famous as well. And you can see this example. This is acetone, and this acetone, what happens is acetone is, this is one structure, but acetone can also exist in this structure, although its presence in the total compound is very less, and because this is very unstable state, and so this, because of the unstable, so one can consider them as a physical state as well. If you increase the temperature, the population of this state will increase, means the more and more compounds will now come in this state. So for example, this is the enol, and what how the enol form will be created from the keto form. This is the ketone, so this is called keto form, and the enol form is what in and all for the alcohol. This is in group that you can see here. In this case, there is no in group, and it's all alcohol. So this is called enol. This is for the keto, the carbonyl group attached to CH3 CH3. The keto enol tautomerism you can also see in the case of aldehydes as well. It doesn't mean that the keto form aldehydes will not show the keto form. The keto enol tautomerism like this CH3CHO. CH3CHO one can also have the keto enol form. And this is what the H group. If this group was the hydrogen atom, this was hydrogen atom, so you can see the keto and this is enol form and the keto form. So anyway, what happens? This hydrogen, the lone pair of this oxygen, abstract this hydrogen atom, and so this not hydrogen, this is a proton, abstract the proton, and so this proton will move here. So the electron, the shared pair is still there, and this shared pair will move here. And as this shared pair will move, what if this means this carbon will have in that case five bonds, but the five bonds with this carbon atom cannot exist with this carbon atom. So this bond will be broken, and anyway this bond should be broken because the oxygen's valency should also be created. Because if this oxygen abstracted this proton, so it will be having OH, the positive charge, and once it pulls out this shared pair electron, that positive charge will be gone. So this compound is a neutral compound. So what we see the transfer of proton as well as electron. So the proton transferred from this carbon atom to this carbonyl atom, and the electron transferred from this between carbon and hydrogen to carbon and carbon. And so here also electron transfer happens. And so in that case, the enol form is formed. Another point is what we know also, that this is what this is we call the nucleophilic center. So nucleophile will attack this group. Any species which is electron rich will look for this center, because this center is having a certain positive charge, although the very partial positive charge, because of the difference in electronegativity between this carbon atom and the oxygen atom. And so because of that, it has a general simple tendency to pull this shared pair electron as well. So this may also drive a little bit this proton transfer and bond electron transfer or electron rearrangement. So this is what is a kind of bond rearrangement. Bond rearrangement, then hydrogen atom's position rearrangement. The position of one hydrogen atom is only rearranged. Generally, enol forms are less stable. This is what one can see in this keto form. The acetone is more stable, and the overall stability, the contributions of this 99.99% of this compound is in the keto form, and so and only 0.01% is in the enol form. So enol form which is less stable. However, there are certain structural factors which can stabilize the enol form as well, and these structural factors are conjugation. So suppose there was already another group here, and this group CH2 and then CH double bond CH3. In that case, this double bond here, suppose H double bond CH2. In that case, this double bond and this double bond will be in the conjugation, the double bond at the alternate positions, and so the extended conjugation will stabilize the enol form. So the enol form's stability will increase. So its overall population of the contribution to the overall structure will be more. Another thing will be the chelation. And chelation is what? It is intramolecular hydrogen bonding, the chelation effect. For example, this compound, this is a keto form. You can see the ketone group, the carbonyl group here and here. Now in the enol form, suppose this carbon is having, because of this carbon atom is positive, having partial positive charge, so it will pull certain this bond shared pair electrons towards itself. So there will be certain partial positive charge here as well. So the carbon atom will is having anyway more electronegativity than the hydrogen atom. So hydrogen atom was having some positive charge, but that positive charge will intensify because of the presence of this carbonyl group, and it will be intensified further because of the presence of the electron withdrawing effect of this group as well. And this is the electron withdrawing group that we call, and what are the electron withdrawing effect or the minus I effect that we will see a bit later. So this is because of electron withdrawing effect, even this hydrogen is also there. So this hydrogen may also move here. This hydrogen may also move there. But the possibility of the hydrogen, there are two hydrogen atoms here. One hydrogen to move here or here is more, because this carbon atom will be having more positive charge, because this is flanked by two different carbonyl groups. And both the carbonyl groups will pull certain electron density from this carbon atom. So it will be having more positive charge, and more positive charge, so it will appear will be reflected as a more positive charge on the hydrogen atoms that are attached to this carbon atom. And so the hydrogen atom will move this hydrogen, not the proton will move here or maybe even here. That is the same, it will give the same formula or same molecule. So suppose it moves here. So it moves here, and what will happen? The bond pair that was here, it will move here to this between this carbon carbon atom, and so this bond will move here. So this will actually be OH, and this OH group will form hydrogen bond with this carbonyl group, and so because of this we call the enol form. And enol form hydrogen is shown between this oxygen and this oxygen atom, not at the one oxygen atom, because the similar structure one can say even if this hydrogen atom moves to this oxygen atom. And so the overall hybrid, and so sometimes it will be attached to this, sometimes it will be attached to this, and this interconversion will keep happening. And so the overall hybrid, the structure of overall hybrid is shown in this way. So this is enol form, and enol form in this case is the major form. And why it is major form? Because of this chelation effect or the intermolecular hydrogen bonding effect. Another effect that increases the stability of the enol form is aromaticity, and this example we see in the case of phenol. Suppose this the ketone, this is an enol form, en and ol form, and the corresponding ketone form will be what? It will be, this will be O, and this group will be CH2 group, and there is no double bond between this carbon and this carbon atom. However, what we see, this ketone form or keto form is very less stable, and almost all the structure will be there in the form of enol form, and this is phenol. So its contribution is almost 100% into the overall structure, and this is the phenol. So what we see, in general the keto form is more stable unless other structural factors such as conjugation, intermolecular hydrogen bonding, or the chelation effect, aromaticity, etc., do not stabilize the enol form. And if these structural factors are not stabilizing the enol form, we will see the keto form is always more stable. Similarly, one can see the tautomerism in the case of other compounds as well. So what we see here, carbon double bond oxygen. There are compounds with the nitrogen double bond oxygen, and the nitrogen double bond oxygen. So these compounds also show the tautomerism, and the equilibrium exists between two different structures. And this form is called a nitroso form, because NO group is called nitroso group, and this is called the oxygen form. So this group, the C double bond N OH, you should remember this is called oxygen. So this C double bond N OH, oxygen. Now the similar things we can see in the case of lactam as well. So amide, you know, CONH group is there. This is called amide, the functional group. And if this amide, it is a cyclic amide, this is we called the lactam. The cyclic amides are lactam. So these cyclic amides can also exist, and they can also show a tautomerism. And so this tautomerism, nitrogen will move, this hydrogen of nitrogen will move from here to here, and so a double bond will exist here, and this there will be a single bond, and you can see here. And this is called lactam and lactine form. These are not very important for you. I am just showing it to have a better understanding of tautomerism. Only you should focus up to here, the keto and enol form. But if such things are given, you should be able to identify the tautomerism, or whether what kind of isomerism is there. So if in this kind of a structural difference you see, you can say that it is a tautomerism. Similarly, amide, you see the lactam, the cyclic amides, a cyclic amides can also show the tautomerism, and this is called amide form, and the tautomeric structure will be imidic form. So this hydrogen, proton of this NH group will move here, and the proton will move here. So this there will be positive charge on this oxygen atom. It will pull this electron density, the shared pair electron. So the charge will be gone, but there will be charge on this carbon atom, and this carbon atom, then it will pull away this shared pair electron which was here, and that can exist as a negative charge, so that negative charge will move. So there will be a double bond, and this is called imidic acid form. The amide form and imidic acid form, they are also tautomers. Similarly, amine and imine. Amine and imine is also a bit important. Some uh, kind of chemical transformation you may see, particularly in the catalytic uh, organocatalytic reactions, where the amine and amine form conversion is important. And so the this is amine form. As you see here, this is NH2 group, and so this is amine, and the NH double bond NH group is called imine form. Any compound having double bond NH, then you can say them as a imine until unless it is not part of the aromatic group. Here there is a nitrogen double bond, but this is the part of the aromatic center, and so this is because of the aromatic cyclic ring. So this is not imine form, but in this case it is imine form. This is in the double bond NH is the imine form, and here in this case what we see, the hydrogen, means the proton moves from this nitrogen atom to this nitrogen atom. So as proton moves, the shared pair electron will move here, this will move there, and so the conversion will happen. Similarly, L-doxime and ketoxime. So this is called L-doxime. Oxime we see, this oximes can be L-doxime and ketoxime. L-doxime is what? If this oxime is because of it was initially the aldehydic form. Here it's more closer to the aldehydic form, this L-doxime and the ketoxime. So what happens if this is carbon double bond O? We know that is a kind of aldehyde if that carbonyl group is attached to hydrogen and alkyl group. So because of the structural similarity of this oxime group with the aldehyde, it is called L-doxime, and because of the structural similarity here with the ketone, it is called ketoxime. So these two names are there. Now let's see the ring chain isomerism. The ring chain isomerism, some people also consider it as a structural isomerism. So in the ring chain isomerism, one isomer has an open chain structure, whereas the another one has a ring structure. So that is why ring and chain. Another compound in the chain, and one compound in chain, another compound is ring. Or the one compound in ring, another compound in chain structure. This example you can see here. CH3, CH double bond CH2. The C3H6 exhibits this. The molecular formula is C3H6. And the C3H6 can have two different structures. And this is propene and this is cyclopropane, and these two compounds are having same molecular formula but different. They are also having different structures, and so they can be considered as a structural isomers, and they generally contain a different number of pi bonds. And you can see here these two compounds, the ring chain isomers, contain different number of pi bonds. This compound do not contain any pi bond, but there is one pi bond in this compound, and so they are having different pi bonds. The corresponding reactant and product of an electrocyclization, these are all electrocyclization reactions, are ring chain isomers of each other. And because of the electrocyclization, the product and reactants in this case are ring chain isomers. The ring chain isomers you can see here. And so what happens, this structure, the number of pi bonds will be different. 2 pi bonds here, 2 pi bonds here, 4 and 1, 5. In this case, you see that only 3 pi bonds are there. So these are the electrocyclization reactions, and such examples. These are all the electrocyclization reaction. In all these cases, what we see, the number of pi bonds in reactant and product are different. This is the intermediate, this is the final product. And in all these cases, you can see this is open structure or the chain structure, this is the ring structure. This is acyclic structure, this is ring structure. Acyclic structure is the chain structure or the open structure. This is also a cyclic structure, and this product is what? This is the ring structure. And so this electrocyclization reactions, the reactants and products are ring chain isomers. Now we will see the stereoisomerism. The stereoisomerism, as we know, the compounds that have the same constitution and a sequence of the covalent bonds. So same constitution and the sequence of covalent bonds are also the same, but that it means what, that they have the same structure, but they differ in the relative positioning, or which we also call the orientations of their atoms up to groups in a space are called stereoisomers. So the structure is same, means the constitution of the, means the carbon, wherever the carbon atom or all the types of atoms are there, their positions will be same, and the covalent bonds, whatever the type of covalent bonds are, they are also same at the same position. Only thing is what, some groups around certain atoms are in different orientation, and because of that different orientation or the relative positions that we call, we see a different type of isomerism, and this type of isomerism is called stereoisomerism. It can be classified as geometrical and optical isomerism, and the examples of geometrical isomerism we will see in details in our next class. And the geometrical, this is the geometrical and optical isomerism. What are the requirements for the geometrical isomerism and what are the requirements for the optical isomerism? Means if how will you recognize a particular compound whether it will show the geometrical isomerism or not? As in these cases, all these cases, by looking at the structures, you can just say that whether this compound is showing a structural isomerism or not. And even if that, what kind of a structural isomerism it is showing, this is definitely open chain and the ring structure. So this is ring chain isomerism. This is tautomerism. Tautomerism, the same compound is two different structural form. It is existing and there is a chemical transformation is always there. It exists in equilibrium. So one can consider this is as the structural isomerism because you see these two different forms are having different structure. And this structures difference in structure is only because of the relative positioning of one proton and the electron. Similarly, metamerism around a functional group, you will see different alkyl groups are attached around or the flanked by particular functional group is flanked by different alkyl groups. So it is metamerism, and just by looking at the structure, you can actually identify it in metamerism. And similarly, the functional group isomerism, all kind of isomerism you can just identify by looking at the structure of this compound, the structural isomerism. Similarly, one can also follow certain rules to understand whether the this to different compounds whether they are showing geometrical isomerism or not, or whether they are showing optical isomerism or not, and what are those rules that we will see in details in our next class. I'll stop here. Okay, goodbye.